So similar to the superposition of electric field strengths, now we are going to talk about the superposition of electric potential. Well, electric potential is actually a scalar. It only has magnitude but not direction. So when we add the electric potential produced by different charges together, we're just concerned about the magnitude. We're just going to, use the plus to connect them together. So in this case, we have again a positive q and minus q prime, which is r1 and r2 from the point P. We are trying to calculate the electric potential at point P. So as we know that the electric potential is equal to kq over r. So the electric potential caused by the positive q at point P is equal to kq over r1. And the electric potential induced by minus q prime is equal to minus kq prime over r2. So the potential at point P is just, kq over r1 plus minus kq prime over r2, which is just kq over r1 minus kq prime over r2. We're just adding them together, in fact. And again, for potential, it does not have a direction. We only concerns the magnitude. And there's another idea, which is the equipotential line. All points on the equipotential line have the same electric potential. So it's just like a contour map of a hill. So all the points on the contour has the same height. So for a point charge, because the electric potential is equal to k big Q, or the central charge, over r, so all points with the same r will have the same electric potential. Therefore, the electric potential lines, as is shown, is like circles or spheres around the Q. And if we have a uniform electric field, the density of the field lines means the magnitude. The equipotential lines will be vertical and parallel to each other in this case. So we could see that the equipotential lines is always perpendicular to the electric field lines, and this always holds true, no matter what kind of electric field we have. The equipotential lines are always perpendicular to the electric field. So now for some special cases about the electric potential. So what if the electric field is uniform, as is shown in the last slide? So the potential difference between 2 points, it was the integral of E times dl from A to B. Well, because the E here is constant, so this integral is merely equal to E times L. As an example, let's try to calculate the speed of particle A when it moves freely from M to N, and the horizontal distance between M and N is 2 meters. So for method 1, let's use the conservation of energy. So because the electric field is uniform and it is equal to the 5 volts per meter, so we just calculate the potential difference between M and N by multiplying E and L. Is the equation that we've just talked about. So the potential difference is equal to 5 volts per meter times 2 meters, which is 10 volts. And as we have learned, the electric potential is equal to the electric potential energy over R. So here we'll calculate the potential energy, which is equal to the change in electric potential times Q. So the change in energy is equal to 10 volts times 0.1 coulomb, which is 1 joule. So because the energy is conserved when the charge is moved freely from M to N, So the decrease in potential energy is all transformed into kinetic energy. And because the object did not have speed at first, the kinetic energy now is equal to 1 joule. And as kinetic energy is equal to mv squared over 2, so we could solve for the speed when the particle reaches n, which is square root of 2 meters per second. And there's also a second method to solve this question, and we'll use the basic Newton's laws here. So as the electric field strength is constant, the force experienced by the particle is also constant and is equal to E, the electric field strength, times Q, the charge of the particle, and it is equal to 5 volts per meter times 0.1 coulomb, which is 0.5 newtons. So the acceleration of the particle is equal to F over m, which is again 0.5 meters per second squared. Well, because we still don't know the time it takes to travel from m to n, so we use the x equals at squared over 2 to solve for the time it takes. So as is shown in the slide, the time is 2 times the square root of 2 seconds. So we could calculate the final speed, which is the acceleration times time, and it is the square root of 2 meters per second. This result is the same as we've done using the conservation of energy.